Hi, everyone, and welcome to today's webinar organized by JetBrains. I'm Paul Everett, PyCharm developer advocate, and I'll be your host. This is a momentous day for us because, Jeremy, we're on Twitch.
Woohoo!
Not just YouTube. I don't know what to do. I'm like one of the cool kids now. The topic for today's webinar is beginner concurrency with async IO. I need this one too, so thanks for Jeremy for giving me some help on this. Today we have Jeremy Schulman, principal software engineer with Major League Baseball, working on the high wire, 25 years in software and networks and the like, 10 years, I believe you told me, exclusively with Python and network automation, and someone who answered my plea for help for some async work I was working on. Welcome, Jeremy.
Thank you. Really appreciate having me on the show. Thank you.
Major League Baseball, huh? What's that? Tell us what you do and what it's like.
Yeah. So I've been with MLB for about 3 years, and my primary focus is all things network automation and integration with our other infrastructure systems. So it's amazing. It's the first time I've actually been on what I would call the customer side. Before MLB, I was 20 plus years at various vendors, big networking vendors, small startups and the like. But this is the first time I've got my fingers, in an actual real production network and really get to appreciate the difference between the theory of network automation when you hear vendors talk about it and the actual practicality of doing it in the real world. So it's a phenomenal experience. I love what I do. I love the people I work with. It's a great place. So it's great.
It's wonderful and lovely for me to talk to an oldster. When you got started, what was like the average backbone speed back then?
I remember starting out with a BBS running, 300 baud out of my house kind of days. So, I'm old school. So, yeah.
So on Python and async, Python's async story has changed a little bit in the last decade. Async IO itself has changed. It's changing again in 3.11. How long have you been using async IO itself?
Yeah, so I started looking at async IO probably around the 3.6 time frame. I started looking at it, investigating it, because I recognized that for network automation purposes, async IO is a really great fit, which we'll talk about in a bit. But I felt that the keywords and the usage and the language was still kind of evolving, is kind of the way I felt about it in 3.6. I mean, they're making some really cool progress, but I really didn't jump in with both feet into the deep end until 3.8. So 3.8, I think, had they formalized a bit more about the language. They had a bit more feature support that made it easier to use. I started to see a lot more third-party libraries supporting async IO about that time frame. So I would say ever since 3.8 came out is probably the time I really started using async IO for all of our work.
You're going to get kind of a gentle introduction into async IO, but what's cool about this webinar is it's going to be with a actual real world example of network hacking, which is funny because you're hacking the network that you're broadcasting from. Is that right?
Well, I won't use the word hacking, but I'm using real networking infrastructure in a real world environment, which, I'll swing a dead cat for the demo gods, but I wanted to do something that, from a real practitioner's point of view. A lot of times, specifically in the network automation field, people are looking for real world use cases and practical things to do. So I'm going to focus on exactly that. We'll touch on just a sliver of theory just to kind of show some of the basics, but we're not going to spend 30 minutes talking about the theory of async IO and the underpinnings of how all the language mechanics work. We're going to really dive right into real world network use cases.
And as far as other resources, I think you have a version of this that you did that's on your YouTube channel. And there's a Great O'Reilly book, kind of thin, that I have on async IO. There's a brand new book just came out last week. I think it's Packed or something, that has a lot of really up-to-date stuff and libraries and things like that. But you pointed out as we were doing prep that Michael Kennedy has a course on async. It's a really good course, video course. And he did a webinar with us a couple of years ago going over that material. And I think you thought that was a pretty good resource, right?
Yeah, yeah. I mean, if you really want to understand the theory of operation, the whys and the hows of async IO and how it compares to, the threading and the multiprocessor kinds of mechanics that we have in Python, he did a really excellent job. He's got some really great visualizations, really highlights, how it works and why it works and the theory of it. He also shows off some pretty cool features of PyCharm to do profiling. So absolutely, that was a great video to watch. It runs about an hour plus. So I'm going to try to be more concise in the practical examples, but he did a great job. And then there's another video series that I mentioned in the resources section later in the deck that, again, is a great video tutorial that's out there.
And plus, with Michael Kennedy, it's that silky smooth Michael Kennedy voice that we've all come to know and love. Yeah. Okay, we'll go ahead and switch over to my slides, go through some pro forma stuff. Foremost, if you have any questions, we try to make this webinar as live and conversational as possible, even though we can't be sitting beside you. We can pretend to be sitting beside you. So should you have any questions or any problems or anything during the webinar, feel free to ask them at any time. Don't wait till the end. Use the chat in YouTube and now, the chat in Twitch. We'll have a few pauses during the webinar where Jeremy will answer some questions, but we'll also try and answer some questions ourselves directly in the chat. So you'll see me look up a little. I'll look to the right because that's where Jeremy is, and I'll look over here because that's where the chat is. So again, if you have any questions, go ahead and ask them. Usually the first question is always, is this thing being recorded? It's my constant joke. I've done like 50 of these webinars. And 1 minute after I say, yes, this will be recorded, yes, it'll be available immediately, somebody will pop into chat and say, hey, is this thing being recorded? So yes, it's being recorded. It's YouTube, so no wait necessary. But we will also announce it on our blog and Twitter and other things like that, so you'll know where it is. All right, we're all set now. Let's begin. Jeremy's going to give us a walkthrough of async IO. What I will do first is, for all of you, I will take the repo for his material, paste it into, I guess I need to paste it into this chat so that it goes to everybody. Is that right? Yep. Oop. Here we go. Hopefully this goes to everybody. That's the URL for Jeremy's repository. And now I'll go over to Jeremy's slides. And Jeremy, this is the first slide. So take it away.
Yeah, thanks. So this will be our agenda for the webcast. Right off the bat, I want to jump into a demonstration of some tools that are in that repo. I love to do like a kind of a turkey dinner cooking show format where I show you the meal as it is you would eat it before we actually go into the process of how do we cook a turkey. So we'll start off right off the bat with a couple of live demos. Then I'm going to spend just a few minutes talking about, why I'm using async IO and when to use async IO versus some of the other multiprocessing or concurrency options. And then we're going to drop right into some live coding. I'm going to do a little bit of the basics of mechanics to introduce some of the keywords and some of the concepts that we'll use, but it'll be just the surface level so that we can get right into a live coding of an example. So you can kind of see how I'll flesh out the coding every single step of the way. And then once we get through those, and we'll take some questions along the way, then we'll reflect on some considerations when we program in async IO. Some things that are good, some things that are challenging, some things to watch out for, but general considerations. And then I've got a little bit of bonus material at the very end. Somebody on Twitter asked for how do you do a thing And so I added one slide on how do you do that thing, and just to kind of show that general topic.
Way to keep the suspense for the end, reward people who stick around.
That's right.
All right. I didn't put this in slideshow mode. Sorry. All right. Next slide.
Yeah. So when do we use Python async IO? Really, it really shines when you're trying to do a lot of IO bound work, right? So if you spend, most of the time in a program waiting for another system to respond, to a request that you're asking for data, that's really its sweet spot. And for network automation practical purposes, we talk about, gathering data from 100 or 1,000 devices in the network. That is a great use case, because really what we're trying to do is gather information from, 100 or 1,000 different, places in parallel or concurrently, and then we process that data. There are workflows that are serial in nature, like do this before you can do that other thing. But a lot of times what we're trying to do in network automation is gather a lot of information, whether that's for reporting purposes, or we need to gather a lot of information to decide where to look next in the network if we're doing some troubleshooting. So there's always this process of just getting a bunch of stuff off the network real quick so that we can figure out what to do. And that lends itself really, really well for the async IO processing model, because it was really developed for, IO bound or IO blocking type of programs. So there was a really good, Stack Overflow discussion on this, which I thought tied it up concisely. Before async IO was around, people would be using threads for this purpose. And then people ask, well, why threads versus async IO? There's a lot of really good material on answering that question. Again, Michael Kennedy did a great job on that, but just to touch on it real quickly, threads are a little bit more process intensive, because it's the operating system that's doing thread context switching, versus in async IO, it's all done within the program. When you program in async IO, there's only one thread. Let me take a step back. I'm going to say a lot of things that are mostly true, whereas Michael Kennedy and other folks will go into the absolute, minutia of the details. So if you're writing a program and you're using async IO, when you write any Python program, it's, there's a single thread. There's the main thread, as they would call it. And so async IO runs in that main thread. So there's really only one thread when you're talking about async IO. And so it's, it's very, very fast, and we're not context switching by the operating system with multi-threading. It's a great place to move from threading to async IO, but there are some considerations that we'll talk about further on. Oh, and the other part of that is, there's a little thing on the slide that talks about, how many things can you do concurrently? I wanted to research that topic. It's like, with async IO, you're bound by the number of open sockets, for example. And so the number of open sockets that you can have on your computer is generally a really, really big number. So, if you have 1,000 network devices and you want to have 1,000 open sockets and, pulling data, right in the wheelhouse of async IO for sure.
All right, next slide.
I think we're going right into the code. No more slides. We'll get back to that one.
All right, we'll get back to that. Okay.
Yeah. All right, so let's go into the demo. The demo repo has a demo script, and the demo script has a couple commands. So one of the things that I wanted to do was, well, let's go off and find out all about all of our transceivers in the network, right? And so I want to figure out, what's my inventory of transceivers. And when I run this, I'm going to go interrogate, about 300 networking devices. And you can see that took about 4 seconds to go interrogate about 300 devices, and gives me an accounting of, where all my transceivers are. And in this case, my program also shows me interfaces that are down that have transceivers. So maybe those transceivers aren't being used anymore, and I can recover them. But that's kind of, again, I'll just run it real quick because it's like almost like a magic show. It happens so fast. That's as fast as it takes to run async IO to talk to 300 devices. just by, but another thing is like running versions. Like you want to know like how many versions do I have running around in my network? So this is going to interrogate all the devices, and it turns out that all these devices are running the same version of code, which, if you do network automation, programs and audits, you kind of want to know what versions of code you've got running around. So it's that fast. I mean, it's literally that fast. The particular coding exercise I want to walk through is trying to find a network attached device. So for example, I'm going to pull one of these. Let's say this device. Let's see, this is a device on our network. I kind of know the answer to the question where it is. So, I'm not cheating. So I can say, let's say I wanted to find this device, find this host by my MAC address. So I would say find host by MAC address. And what this is doing is it's going to find, where that MAC address lives on my network. And that basically said, I found this MAC address, it's on this switch and it's on this port. So, for example, maybe this is a printer and we don't know where it is. Somebody moved it around, or maybe it's a phone, VoIP phone, somebody moved it around. We want to know where it is. But this is a pretty, common use case of find a thing on a network. How this process begins, somebody could say, well, I have an IP address, and then you have to find its MAC address. I'm not going to kind of go through all the minutia of being a network engineer, but every end host on the network has a MAC address. So I figured we'd focus, on that. And what you'll also notice here is that the program terminated early. Like I didn't have to go through all my devices. It stopped when it found the device I was looking for. So there are different types of use cases that we have when we're doing, network automation things. We could, look for a thing and stop when we find it, or maybe we're just trying to do an audit or a collection from a bunch of different devices. Those two use cases I'm going to cover in our coding, our live coding exercise that we'll start now. So we'll jump into it. But that was the demo portion of the show to begin with. Groovy?
Hey, can I ask you a quick question?
Yeah.
The things that you were just writing, some of them kind of look like one-off things. How often in your job are you reusing something that you've written versus I need this one task and I'm just going to write a script?
Yeah, that's a good question. There are some things that we do a lot, and then there's some things that we don't do a lot. The interesting thing about networking is it's really a distributed systems problem, where your distributed system is a bunch of vendors who don't like each other, trying to interrupt protocols that are supposed to work together, but sometimes don't. Sometimes you're writing troubleshooting scripts that are very one-offy,
Okay.
And then other times you're writing audit scripts, like, every year, we have to audit the network to look for, say, optics that we're not using anymore, or whatever the case may be.
Because as we get into your code, Python can be a really great vehicle if it's just a one-off script that doesn't need a virtual environment and only uses stuff in the standard library. You're going to have that everywhere.
Yeah. I think, what we'll find is, as network automation finds its way to more and more companies, there are always going to be one-off needs. My general philosophy is, buy commercial products when we can, because, I don't want to be writing to reinvent the wheel. But there's always these weird little corner cases that network automation or network engineers find themselves in, or there are features about your network that you specifically need that maybe a commercial tool doesn't support. And so there's always going to be, what I call the buy, beg, build kind of formula. It's like, buy what you can, if your company has budget, beg off the internet, for open source projects, for things that, you can't buy. And as a last resort, I try to, write code for special purposes. All right. Thanks for that question. That was good. All right. So let's get right into it. I'm going to use IPython just to do a little bit of demonstration work. So this is IPython. I just have an alias called PY because I'm lazy and I don't like typing IPython. We're running 3.8. So everything I'm doing here is in the context of 3.8. And so I'm going to start out with just presuming, folks on the webcast haven't seen async IO. So let's just start with, def foo, return 1. And if I do like, what is foo? It's a function, right? And if I call foo, it returns me the value at that time. Now with async IO, there's this new keyword called async def, and I'm gonna, say return the value to. Now async as a keyword indicates that this is a coroutine or something that is part of the asynchronous execution environment. And if I do a type on bar, it is also a function, right? So it is a function. But when you call bar, and I'm just going to assign this to a variable x so I can play with it. If I call bar, what x gives me back is what's called a coroutine. It doesn't give me the value of 2. It is a coroutine, okay? And what a coroutine is, it's a cooperative routine, meaning functions that are defined as async cooperate with one another to provide the concurrency that you want out of your program. And so that's why you might hear the term cooperative multiprocessing or cooperative concurrency. Now, to get the result of a coroutine, you have to await the value, right? So most of the time, what you would see in code is await bar, await some function. And we're going to see a lot of that. Now, I am in this, interactive interpreter, but generally speaking, you can only await on something if you are in an async function, right? So generally speaking, you just can't say await bar out in kind of like this cold area of programming space. What you would typically have to do is, and typically what I do is I'll have a function called main, and very silly. And then when you want to run, basically when you want to kick off and run a program, what you're going to do is you're going to use the async IO library, say async IO run, and that's going to, run your async program. Now, before version 3.8, there was some other mechanics that you'd have to do. It wasn't as clean as just async IO run. So I'm not going to go into the history of all that, but you'll see me use async IO run in the code demo so that it starts the process. Okay. So my demonstration code uses a CLI tool called click, and click, or the CLI code you'll see it run async IO. All right. So I'm going to take a pause here just to see if anybody's got questions about the very basic, very veneer level of the material that I'm trying to cover here to introduce these keywords, async and await.
No questions yet. And this is a really good format to do it in IPython and really help people remember that that thing that has async in front of it is a thing that when it's called turns into a thing. And your other point about you have to put in await inside something marked with async. Tooling will help remind you if you get that wrong.
That's right. That's right. Yeah. My first piece of advice to anybody who's starting out in programming is get a real IDE. PyCharm is a great example. There are others. But if you are programming, starting from a text editor or Notepad or VI, it's a lot, in my opinion. Everybody's got their flavor of things. But in my opinion, if you're just starting out, invest in a good IDE.
But CI tools also will tell you.
What's that?
CI tools will also tell you.
Yeah. Okay. So let's get into some actual practical programming.
Sorry, real quick. We have one just come in from Mark. Apologies for the interruption. Does the coroutine equate to promise in JavaScript? This is an interesting point.
Yeah. So straight off, I'm not a JavaScript programmer, but conceptually, I would make that analogy. It's basically saying this is something that needs to be done in the future, right? So really, I would call it a future, and Python, the language, they call these things futures. You know, there are awaitables and there are futures and there are tasks. But if I were to, for example, create a function, you know, foo, and then call foo, but don't await it, you'll see that you get this kind of error saying, hey, man, you promised, to use his language, you promised to run this coroutine in the future, but you never really did. So it wasn't awaited, right? And that's why you might see these types of errors from time to time. You know, coroutine foo was never awaited. So to me, it is a lot like a promise. But again, I've never.
An interesting sidebar on it, though, is that JavaScript and TypeScript added async and await as the successor to promise-based callback programming, and it was inspired by Python's adoption of it.
Yeah. Well, there's always, you know, standing on the shoulders of giants everywhere. Yeah. So it's good. It's good. All right. Any other questions before we jump in?
No, there's a point from Sasha about is this a really good fit for downloading thousands of small files? And yes, that's almost a perfect example. And Michael Kennedy's webinar showed the before and after effect of this.
Yeah, absolutely. Okay, so let's get into some code. All right. So what you'll see here is the code in the CLI for running the find MAC address. And you can see that, you know, this is Click. If you're not familiar with Click, it's a great CLI building tool. And here you can see I'm calling asyncio run, and it's going in this module called find MAC adder. That's the module, and in that module, there's a main. And if I were to jump over to that, and I'll make this a little bit bigger, you can see that it's an async def kind of structure. Okay. So we are going to rebuild this code live and on stage for your viewing entertainment. Okay. So what I'm going to do is I'm going to just kind of copy paste this little bit here. And just to make another version of it, I'm going to call this, oops, I missed the very top one. I'm going to call this live find host. And just fix that, live find host. Okay. So I've made a new command, and if I go over here and do demo -- help, I should see live find host. Now, I don't want to use the one that I've got. I won't even be clever, right? Okay. So now what I want to do is I want to create a brand new function in a brand new file. So I'm just going to go over and I'm going to create a new file called live find host. And I will make this bigger. And I will say async def main inventory and MAC adder. Just to give it a placeholder, no magic here. And because I'm going to cheat with both hands, I'm just going to do something like this from .import live find host and do live find host main. Okay, no real magic there. But if we just want to see it working, I can just say, you know, oh, hi, live demo. Right. Very exciting. Okay. So for here, I can just do demo, live find host. And I have to give it a MAC address because that's what the program wants. So I will put one here. And it says, oh, you didn't pass it inventory. So I got to go and fix my code. Right. Inventory. Oh.
Positional versus keyword argument strikes again.
Oh, no. What is it? It's inventory. What am I doing wrong? Okay, Mr. Jeremy, what are you doing wrong? Live find host, right? All right. let's just copy this because I don't like to do all that. All right, so let me import a couple of things here from typing import list. I'm a big fan of using type hinting, and there's a library called MacAdder that I use to deal with MAC addresses.
Huh.
Okay, and so let's try that again. That's weird. When I did this for real, of course, you know, everything works just fine. And then when you do it on a demo, it doesn't work. What am I doing? Oh.
You're missing the click decorator.
I am missing the click. Well, that's here.
That's what someone, Durala in chat saying.
What's that? Here?
Not passing the option decorator.
No. Let's see. I'll tell you what. What if I just did... What if I just did this? Let's get rid of that. And I'll just swap it out. Because that should be the same. Okay, let's just swap it out. Like my everyday. Okay. You know, copy and paste coding errors. We'll just move on, right? Let's not debug. All right, so I just kind of swapped that out. So we are here now. All right, mystery deferred. I'll call it that way. Now, if I want to, you know, look at one device, right? This is the way I think about it. It's like, okay, if I'm going to do something in parallel, well, let's figure out, or concurrently, let's do the one thing first. So if I wanted to do a function that says, you know, check one device, for example, I'm going to give it the device name and the MAC address that I want to find. Okay. So this inventory is really just a list of devices. You know, these are just host names that I can, you know, reach out and touch. And so if I want to touch them, I need a construct, and this is where the async IO happens. I'm going to say from Arista, so I'm using a bunch of Arista devices, import a device class. Now, this device class is a subclass of the HTTPX async IO client, right? And that's something very important to mention here. There are many ways in which you can asynchronously communicate via HTTP. I like to use HTTPX. You know, your mileage may vary, your choices can change, but in general, there are libraries to do this. And one of the nice features of those libraries is you can create what's called a context manager. So it will open a connection, do a bunch of stuff, and then close down that connection. So in order to do that, we have to say async with, right, which is the asynchronous connection manager. And I'm going to say the device's host name is device, and that's going to give me a variable to play with. And so now inside this block here, I'm in an open connection, essentially, with that device. I'm going to make that the ability. Now, PyCharm has a nice way of doing type hinting. So I'm going to say this is a device. So I can say device dot. And this class that I've created has a method that I've created called find MAC address. And I'm going to say MacAdder is equal to MacAdder. And you'll notice that I get the squiggly because this is a awaitable. So I have to await its result. And what it gives me is, what it's supposed to give me is, this function returns the interface name if the given MAC address is found on the device. And if the MAC address is not found, then return none. Okay, so I don't know if that shows up in the webcast. It's pretty small, but I'm going to say interface is equal to this, right? And this says, you know, this is going to tell me whether or not the interface exists. And if it does exist, then I want to return a value. Otherwise, I want to return none. So I could say if the interface exists, and I'm using the Walworth operator in 3.8, which is another reason why I like 3.8, because I can be a C programmer again and do this. I can say return the device and the interface. So I'm basically returning the context of the result, right? I'm saying I found it on this device in this interface. And if I didn't find it, return none. Okay. Now there's going to be more here, but let's just start with this. All right. So far, so good? All right. So now what we can do is we can say, all right, let's check one device. And let's say that the device is inventory, the first one in the inventory, and we're going to pass it the MAC address. Okay, great. Now we can see that, again, we have to await that to get a response. So let's do result and just print result. Now, I'm only checking one. I'm sure it's not going to be there, but you know, it said locating switch port blah, and it just returned none, basically because it's not there, right? Now we could do, you know, a bunch of these. We're not doing them concurrently now. This is kind of an important thing to note. You know, it's like, this is not what you would do, but I'm just showing you kind of the bits of it. So I'm doing 3 of them. Oh, and it found it actually on that one. That's kind of funny. Okay, so we'll get back to this. I found it on the 3rd one. Maybe I should choose another example. Let's choose another example so I don't find it. Okay, none. All right. Now, if I wanted to run all of these at the same time, this is where we get into the concept of concurrency. So what I can do is async IO, and I'm going to show a couple different options here. Async IO has a function called gather. And what gather allows you to do is say, I've got a bunch of coroutines, like say this one, and this one, and this one. But you have to wait it. Now what this does is it says, I'm going to run all these 3 things concurrently and get you back a result. Now it'll give you a result for each one of these coroutine calls. So if I print the result, I'm going to get a list. Oh, I got none. That was me backspacing. That wasn't a bug. So I got none. Okay. Well, let's say that I want to look across my entire inventory, all of them, right? But you can see that the way gather works is it takes an iterable, you know, it takes a, you know, kind of a comma separated list. But the general pattern here is we want to create like a list of things. So I could say for device in inventory, I want to check one device, right? So device equal to device, and the MAC address is the same for all of them. Okay, so now I have a list of tasks, right? And then I could say splat tasks, because the splat operator is the way to flatten a list into a comma separated thing. And now what I expect that I'm going to get is a whole bunch of results, one for every item in the inventory. So let's go do that. And, you know, I don't have my fancy progress bar here, but we'll add that later. But you can see that there's a whole bunch of nones, and then I see some results, right? I actually see multiple results. Now, in networking land, a MAC address might show up on multiple interfaces, some of which are network interconnect ports. So that's what I'm seeing here with these port channels. So what I want to do is I want to update my code here that says, okay, not only do I find an interface, but it also has to be on an edge port, right? So I need to say, is this an edge port for this interface? And if it's not an edge port, then return none, right? So we'll change the logic a little bit. We can say, you know, if we don't find an interface, return none. And if it's not on an edge port, we found it, but it's not on an edge port, then return none. Otherwise, then we return it. Okay. Good.
When you get a chance, we have a great pile up of really good questions.
Okay.
So whenever you get to the next stop.
Okay. I'll do one more thing. And so now you can see, like, Let me clear the screen so it's actually more obvious. Actually, let's do this real quick. For each in result.
While he's doing the typing here, I will note that this segment is really interesting to me, this kind of programming model of gathering a bunch of things, kicking them off, and as they come in, things happen. It really changes your programming style.
Okay, so here it is. There's the one answer, right? Here's the one answer. You can see like it's buried in a bunch of nones. Okay. Now, I'm going to do one more thing just to get it out, and then we'll take a pause. So I have all these results, and I only want the one that's not none, obviously, right? So I could say, filter by none my results, and found is equal to this. And filter is basically going to apply the none filter to these results, basically weeding out anything that's none. And then I'm going to take the next from that iterable, because filter returns an iterable. And in the off chance that it wasn't found at all, I have to give it a default value. And then I can just say, print found. Or not found. So this is going to go do its thing. And it basically returned the result, kind of weeded out all those nones. But there's a, I'm going to take a pause in just a sec. But the reason why, this is not the approach that I would use, but I wanted to show it, is because we want to stop when we found it. And there's all these other nones after the fact that we don't really care about. I mean, it happens so quickly, you could argue, well, it doesn't really matter. It depends, but I'm showing a technique. All right, I'll stop here and we can answer some questions.
Okay, first, I wake up in terror thinking JetBrains is going to ask me a basic competency question of what's the difference between an iterator and an iterable? And I'm going to go, and they're going to fire me on the spot for not knowing such a basic Python thing. Okay, these are some good questions. Try not to get too deep into them because we have 8. How do you combine async IO with logging? They're using Log Guru. This is not this is a legit question.
Yeah. So I had the same question when I first started out too, and there was a Python package called AIO Logger or AIO logging that can be used for that, because one of the considerations that I was going to talk about later, but we can talk about now, is file system manipulation is IO, but reading and writing from the file system, it turns out, is not part of the Python standard library feature set. So there is a way in which you have to handle that problem, and the answer is they wrap it around a thread, basically. So they spawn out another thread to actually go do the IO to the file system. Logging basically is kind of the next thing of that, on top of a file system. So AIO logging is a library that wraps threading around a logging mechanism so that you can use logging, and it basically will write a log file as a background thread, and that's how they do that. Yeah.
I saw something similar with os.scan being in a thread pool or something like that. Okay.
Yeah.
In which contexts do you use yield versus return under async IO context?
Yeah, that's a great question. It's using async generators is what that is technically called, has a place of use. I will give you the example where I use it. I have a chat ops system, so with Slack, we have a chat ops system that you can say, hey, show me the status of, this network device or whatever. And so what it does, or bounce port is a very common use case in that. And so what happens is when a user executes bounce port on chat ops and the backend decides to go process that, as it's processing the command, like the first thing is to say, shut down the port, then it yields, an indication to the user, so they know, hey, I shut down this port, and so in the Slack, I'll say shutting down port, waiting 10 seconds. And then we do a sleep, and then we, do another yield of a message saying, I brought the interface back up, so it gives a very nice user response, user experience. So they're not like waiting to the end. It's like bounce port, and then it kind of goes off into a black hole. So yielding is a way to give that kind of real-time experience. And you can use them with async with async. They're called async generators. That's one way I use that. There's many others, but I thought that was the most interesting one that I've used.
This book,
has
a really good section on async generators, not just as a memory efficiency tool, but as a simplify your programming, which I thought was pretty interesting. Okay. Can you use async IO as a small specific part of a larger application?
Yeah, absolutely. As I said at the very beginning, the async loop, the thing that actually runs or drives all these coroutines, sits within a thread. Now, you could theoretically have multiple threads in your program, and each of them could have their own async IO loop that are separate from one another running around. Threading might not be the best practical use there, because again, threading in Python is bound by the GIL, which some people make a lot more noise about than it's real practical. Again, Michael Kennedy does a great discussion on that. But if you wanted to use multiprocessing, right, then you could have multiple processes each running an async. Oh, I thought of that for this demo, so let's take a look at that, right? So whoever asked that question, thanks for the shill. So I did implement a multiprocessor version. So essentially, I took the async IO method that basically pulls the transceiver, and I took my inventory and I chopped it into 4 pieces, and then I launched it into a multiprocessor pool. And I thought, well, maybe that'll make it go a lot faster. I was just curious. So this is what that looks like. So you can see that each chunk has 73 blocks in it. And, it doesn't really feel like it's any better, because there is overhead when you have to, launch OS processes and kind of communicate the data back. And there's all this kind of overhead. And one of the benefits that I like around async IO is you can launch all of these tasks, because that's what they're really called. And the way you get data back from your tasks is a different mental model than when you're dealing with threads and processes. You have kind of to like pipe data through queues and join them in a weird way. Well, not a weird way, but just in a way that makes you have to think about it a lot more than with async IO. You can just say, hey, run all these tasks or these coroutines and give me the data. It's all in the same. When you're using async IO, it's all in the same thread, basically. So it's a lot easier to get data and debug that type of program. I kind of wandered there. Sorry about that.
I'll also point out, just yesterday, Michael Kennedy had a tweet about that well-known idea that you can't get half pregnant with async IO. As soon as you start, you got to rewrite all your code to be async and await and everything. And so he did a little library, or just an example of letting synchronous and asynchronous code coexist. There are lots of libraries out that do that as well. Fast API has it built in.
Yeah. I was going to talk a little bit about that in the considerations part.
Okay, good. Do you want to keep going through questions, or you want to get back to your code?
Let's do one more question, and then we'll kind of do a little bit more code, and we'll jump back into some more questions.
Okay, so what I'll do is I'll do like 4 questions fast. In terms of memory, how are these async maintained? That's one of the issues, is there's no free lunch. Switching to async does have a little bit of memory overhead.
Well, like any kind of concurrency, whether it's threads or async IO, there's a programming model where each of those, things, we'll call it a task just to give it a name. They all have their kind of a data structure, and they have a memory footprint. And then we talk about the amount of processing that it takes to swap between those tasks. There's no free lunch, but if the question is about, does it blow up your memory usage, or not, that's a very difficult question to answer because it depends on what you're building.
Because we're 40 years into Berkeley sockets. And so you're sitting on top of a thing, on top of a thing, on top of a thing, on top of a thing that has all these little effects that interact with each other, threads and things like that. So it is difficult to answer. Go back to, well, actually, one last one, and then I'll answer the rest. What are the challenges when debugging async code?
I actually find it much, much simpler than trying to debug the equivalent in multi-threading because you can set a breakpoint. You can literally set a breakpoint in any async task, and then it stops, right? Yeah. You don't have all these other things kind of running around and gerrymandering, your data.
This book has a really good example of you run code once and get a different answer when you wrote it again because of thread effects.
Yeah. Yeah. So I feel that the programming model, kind of once you, cut bait and go into the async IO model is much, much easier to develop in, for sure. But it does come at some other constraints. So, all right, next question.
All right, go back to your code. I'll answer the rest.
All right. So, where we left off was I was running all of them all at once, waiting for everything to finish. And I don't want to do that. I basically want to, run until I find my answer and then stop. So how do we do that? Well, I have these tasks, or I have these coroutines. And just kind of, just for the sake of argument, I'll put a breakpoint here. Okay, and then I'll run my code here. So I'm here. Breakpoint. It's great. All right. And if I look at one of my tasks, this is a coroutine. Now, what under the hood is happening is that what we need to do is they need to be a future or a task so that they're put on the event loop. And so when I was making the call to async IO gather, for example, it was taking all my coroutines and saying, hey, man, if you're not a coroutine, I'm going to turn you into a task so that I can do whatever I need to do. But let's do that correctly, because there's a reason why I want to do that. So let's say that I want to turn this into a task, and I'm going to say async IO create task. Now this is doing two things actually, and this is very cool. The first thing is it's taking that coroutine and it's turning it into a task, which allows me to do things with that task that you can't do to a coroutine, like for example, cancel a task. Right? I mean, you can't cancel a coroutine, but you can cancel a task. Like those are things that you can do, right? Now, it's going to turn it into a task, but simultaneously, it's adding that task to the event queue for processing. So right now, when I run this code, all these things are now immediately on the event loop for processing. Now, they're not processing until I say, hey, man, go ahead and do that. But let's take a break out of here and this now. So now if I look at tasks, you can see that this is a task now, and it's in a pending state, which means it hasn't been put on the queue for processing. And you can kind of see, where it is and what it's doing. All right, well, let's exit out of that. So now that I have these tasks, I could say, for task in tasks. So I want to loop through these tasks. And well, let's say each device. Like so, for every device that's in my task list, I'm going to get a result. I'm going to await. Right? So now I can await on that task, which is going to give me the result as they are happening. So no longer do I have to wait for everything to be done, which is what gather does. And a lot of times, gather might be the right thing to do. No, but in this case, it's not. So now I can do this, print result. And now we can run this again. And so you can see like it was kind of, spitting them out a little bit at a time. And we have a whole bunch of nuns here. right? It's hard to see where the actual one is because of the way I'm scrolling, but it's in here. There it was. All right, I'm not gonna like hunt for it. Let's do this. So we can say, for example, if we have a result, we're done, right? We can say break. Else we can say result is none. And we could say, you know, print result. So basically, this is your for loop that says if I find it, I'm done. If I hit the end of my loop, I didn't find it, so it's none. All right. Say, you know, not found. So, you know, we're not seeing any, you know, progress, right? So we want to see a little bit of progress. Well, what if I want to know how many places it checked before I got that output? You know, you could use enumerate, right? You can say, you know, count. I'm going to ignore my coding error for that for a minute. But this will basically say, you know, how many places did I look? It says I looked at 181 places. I got a response back from 181 places before I found it, right? If I run this multiple times, I'm probably going to get, you know, multiple different results, you know. Well, in this case, I got 181 again. That's interesting why I keep getting the same number. Sometimes you will, and sometimes you won't. But that's interesting. All right. So another way to do this is, I want to show one other way to do this. There's another mechanism in async IO called asCompleted. Okay. So I could say for each dev in async IO asCompleted, and here you're going to give it the tasks. Same thing, you know, result is equal to each device await, you know, and you can say, you know, if result and kind of trick, break, else. So this is another thing. Now, what asCompleted does is much like gather, if you didn't give it tasks, it will automatically wrap it for you. So you could go back to doing this, for example. So I get that answer. Now, if I wanted to, you know, as we say, stroke the user and let them know what's going on, we can add, you know, a pretty type of progress bar. I like to use a package called Rich, which is, you know, really awesome. Yeah, so I'm going to just add that very quickly so you can kind of see the process. I'm going to say with progress bar as bar, which gives me a progress bar. And a progress bar can have multiple tasks. So I can say add task, and we can say looking I'll say that's a dot, and there's a total of this number of tasks. And as it's doing that, I could say bar update the I'll say call this a bar task. This is how Rich works. I'm going to say update the bar task.
Hey, is your line 23 needs to be indented one more? It's not under the if. The else should be under the if.
This one right here?
Yeah.
Now this is the else for the for loop.
It's for the for. Okay. All right.
Yeah. Basically, this is what says if I've entered.
Short.
Yeah. Okay.
Sorry.
Oh, now we can do this. And now we got a nice little progress bar. And you can see like that one completed, you know, at step 82, for example. And we kind of bounced out at step 82. This tells you like how much time it took, you know, to find it. So this is one more, you know, way to do. I want to go through a collection of tasks until they happen. You know, Or, I didn't have to bop out. If I just wanted to have something that just indicates to the user, hey man, don't get impatient. Like for example, the demo for the transceivers, I don't exit early. I just want to have a nice little progress bar so that somebody knows what's going on, that kind of a thing. So progress bars are great to give your folks a good user experience. And then you have options with async IO, whether or not you want to kind of wait for all your things to be done, or you want to do something as they are being processed and completed. That is the end of the live coding demo portion of our show. That's as much as I wanted to cover, at least. There's a lot here actually, but hopefully it gave people enough of a sense of a couple different options, and just enough about async IO to kind of start playing around. I do want to say that going back to an earlier question about other libraries and such, for network automation in particular, there are a couple of really good libraries out there. One is called Scraply, and Scraply inherently supports async IO, for doing SSH. So it has an async. It's built on top of async SSH. I cannot remember the gentleman's name who wrote that, which is a brilliant piece of software. And so there are now options. Again, 2 years ago, not so many libraries, for async IO processing. Now there's a lot more available. All right, questions, final round.
Final round. There are two related questions. I gave a shot at answering them, but you could talk about it a little bit. This idea that I've got a whole bunch of tasks and they're going to kind of run autonomously, and maybe they're generators and sending results back and stuff like that. But then the mothership wants to shut everybody down or shut just one of them down or whatever. How does the event loop or even the operating system signals talk to a task while it's running? Yeah.
So great question. As a task, and I'll do this in the code so that people can kind of see it. I'll turn these back into tasks. All right. So if we look at one of these tasks, let's say T. Okay. You can see that there is something called cancel, right? Now you can call cancel, and what happens is when a task is marked as cancel, it will raise a specific exception. And this is actually, I'm glad somebody asked this because this is a really important point. There is something in async IO called async IO canceled error, right? So this kind of gets raised, okay? And that's how things get bopped out of, that's how we instruct the loop basically to, kick it out. You can trap for that. Like, you can see like, as I'm running something, did it get canceled? So let's just, I don't know. I didn't test this out as a demonstration, but if I said, tasks 5 cancel, we ran this. Not really sure what's going to happen, but let's find out. Just curious. Yeah, so you see like there was a canceled error, right? And you could even trap for that because what happens is this await, when you do this await, that's when something is happening. So if I were to break this out, not be so fancy, if result. You can then actually put your try catch around. So I'm going to do this and then it's not going to work. So I want you to know that up front. Okay, so I'm going to try to catch that cancel error. Didn't catch it. You're like, huh, why is that, Mr. Jeremy? Well, the answer is because async IO canceled error is not a subclass of exception. You'll notice that it's a subclass of error. So that's something that really kind of bit me a while back. So if I wanted to catch this, now I'm in the breakpoint. right? You can see like I'm in the breakpoint, but because I have my progress bar going, it makes it a little annoying to actually do something. So I'm just going to exit out here.
Hey, a few more came in as you were working on this. First, on your line, the line you're on right now, that doesn't look like an async iterable. So the things that are happening inside of it are happening, I guess, synchronously, but then the things that they're calling might be synchronous.
Well,
Async, I mean.
Yeah. So just to kind of review a little bit, I'm in this function called async main. So
Got it.
this whole program is running in, the context of an asynchronous, an asynchronous task. However, the person who asked the question was correct. Async IO as completed returns an iterable, not an async iterable, which is why you have to await the thing that it returns. Okay. If you were actually to drill in this code and examine it carefully, it's a bunch of kind of internal plumbing. But normally, like if you had a generator that was an async generator, it would be async for, and that would be a correct thing to do. That is an artifact of the way this works. Yep. So if we went back to, so it's the same thing like this. Like if I did for each of these in the tasks is just an iterable. It's a list, right? Which is why I have to kind of await on it, right? Yep. Same kind of deal.
We actually have a couple of questions from Twitch.
Okay.
Let's see. If I have a job like find the next job to handle and it needs to run live, as in can't get the next 1,000 jobs and add to a queue, how can I run something like run 10 at a time? And for each of those synchronous, lock and get the next job. So you've got a queue, and I guess the batches are synchronous, but you want to get them in asynchronous batches or something.
Yeah. I had the exact same question. Like I wanted to do the exact same thing. And I Googled for this. And basically what I wanted was an as completed with a batch, like a batch number. It turns out that somebody on the internet wrote that exact piece of code. And I cleverly copied it and modified it for my own use. And I can't cite the source because I didn't prepare for that. But it did exist. And without going into too much detail, but if I click into as completed, what you'll notice in here is that it's doing a whole bunch of queuing. It's like it creates a queue and it goes through some processing and has all this, stuff in here that, is basically running it through a queue. And the person who wrote the batch version of as completed, used the same mechanisms, kind of these kind of consumer producer queue with a batching semaphore, I think. Because I don't remember it directly, but that code does exist. So if you Google for it, you should find it. And if you don't, we can try to. I can provide the reference to it.
I find that stuff fascinating, and it gives me a brain cramp.
Yeah, it is pretty fascinating. I learn something new about Python almost every day. It's just crazy. Yeah.
Okay, another question from Carl R. Dev on Twitch. We talked about a little bit before on groups. Are the tasks isolated? So if one task throws an error, 500 HTTP error, it doesn't affect the other tasks?
Well, the answer kind of it depends, right? You notice like if I had an error, I could put a try except around each of them, right? So I could trap them like I did before. Like here. Whatever.
Right.
If you're using the async IO gather, it actually has a feature where you could say return exceptions is true. And so what happens is if you do this, your results list might have exceptions in it, and then you kind of have to look for them.
Yeah, right.
So if the question is I've got a bunch of async tasks and one of them might throw an exception and I want to catch it and handle it, you can absolutely, treat that situation, very effectively. And this goes back to why I like async IO over threading, because for those cases where you want to like drop into the debugger and kind of look around, it makes it so much easier to do that. It's ridiculously easier to do that.
That's a very good point.
Dealing with all the threading stuff. Yeah.
Life with threads is a tough life.
Yeah, you know, well, I mean, if all you have is a thread, then every problem is threading. Every solution.
Okay, let's see. This will be the last question. Async IO is limited to one machine. Isn't Celery and etc.? Isn't that better as you can spread the load? Multifaceted answer coming.
Yeah. You know, better is always, it depends. You know, you can combine, like I showed with the demo, you can combine these techniques together. You know, I did the transceiver collection as a multi-core, you know, kind of thing where I chopped up the inventory into, you know, 4 pieces and then let it run on actual, you know, multiple cores on my one CPU. You know, you can do that. Celery as a background processor is great, you know, for a lot of use cases. Like, for example, you know, if you have your worker processes on different machines, you know, for example, Celery is a message queuing system. You can get, you know, you could do that. Or even if it was on the same machine, you know, you could, you know, decide how you want each of those background processors to work so that you're not, quote, locked into everything is async, you know, turtles all the way down, like, you know, Michael Kennedy said about being half pregnant. Right. So, you know, there is no right or wrong answer. You know, there is no, this is always better and that is always worse. It's you look at the software that you're trying to develop and the constraints that you have and the performance objectives that you're trying to reach, and you choose technology accordingly.
And the complexity, because you could do Dask, you could do Celery, you could do Redis, you could do Memcache, all these other things, but that's more infrastructure to manage. Yeah. And so I just pasted a link to AIO processing, which lets you keep the async IO model and use the multiprocessing library to have sub-processes that can be scheduled and coordinated with queues and things like they were async IO's things. Yeah,
but if you just want to use like run a sub-process asynchronously, you can do that with async IO. It's like, and I do this because this is how I run ping, because I'm really lazy. I do, you know, you can do create sub-process shell. Like, and I can, you know, do ping, you know, target, whatever. So if I wanted to like ping 30 devices concurrently, I would just, you know, following the same kind of formula here, just create a bunch of tasks with these sub-process shells and go, and, you know, done, you know. So you can do a bunch of sub-processes concurrently just out of the box with async IO. If you want to do something fancy, you know, like, as you
internet scale,
you can, you know, again, what I'm trying to do is show the use of async IO for the network automation community, that shows them you don't have to use all of these threading queues and all this complex, you know, computational theory or computer science to get at the meat of the problem that you're trying to solve. I mean, yes, you need to like kind of jump into the async IO world, but the benefit of, you know, wading in, you know, and doing it is a lot. You know, I think there's a lot of benefit for doing that for some of the things we've talked about, like debugging and, you know, running things concurrently faster without, you know, trying to deal with all the other concurrency, you know, goo that predates using async IO.
Sure. And I just pasted a link, and we'll get out of this, but I just pasted a link to the repo where Sam Gross has been working for 2 years on his no-gill fork of Python. Fascinating project, and it has very promising results for using multiple cores without having to radically change your Python programming model.
Groovy.
Okay, Jeremy, you wanted to, we're going to switch back over to my computer to go to your last slide. Is that correct?
Yep.
Okay. All right, let's do that switch, and we'll go into slideshow. Take it away.
Oh yeah. So this is like, some people ask me, well, what's a great way to get started? The video series that I show there was probably the way I got into programming in async IO the best. This is a 6-part series. It is phenomenal. It's like each of them are maybe like an hour or so long, and they build on one on top of each other. The gentleman who developed this, I'm sure I can't say his name.
Luca Schlonga.
Yeah, he is, an incredible presenter. He's also, the developer in residence for CPython. He's part of a company that, called EdgeDB, I think, that makes a really cool database. I mean, I learned from this guy. And after I got through his video series, I'm like, I got this. If you're the video kind of watching person, I am. This is the book you mentioned, Using asyncio in Python. It's a really good book if you like reading books, which I also like to do. And then you had mentioned another book that just came out. And so since I like books, I would like to know what that book is so I can go buy it. Because the challenge historically has been, like you said, there wasn't a lot of modern information about async IO. Like back in the day, I have a book called Fluent Python, but it covers like up to 3.4. And so it doesn't cover all the really cool bits. And so I've been waiting for some really, really great async IO, documentation, because there's a lot of, you can build really complex concurrent systems. And if you have to build that kind of software, that's really, really cool to do. But you need to understand how all these concepts work together. And there really isn't a good body of documentation that shows, here's how you design and develop concurrent systems with async IO that leverages, well, when do you use a queue? When do you use the semaphore? And how do you use these things to do blah, 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 blah. And having a book like that,
the modern Python semantics.
Yeah. So if that's that book, man, I would love to know which one it is, and I will go buy it.
All right, great. Okay, well, I will switch back over to my slides and get us out of here. All right. Okay, well, thanks, Jeremy. This was fantastic. We had a lot of interaction on this. Thanks for taking the time to talk with us about async IO and network automation. If any of you have any questions later, don't hesitate to reach out to us, reach out to Jeremy. Just put something out on Twitter. You'll get a lot of great answers. And let us know what you think about this webinar and any other ideas related to async IO that you'd like us to present. If you'd like to get more information on PyCharm, well, thank you so much for asking. Please go to our website at jetbrains.com/PyCharm. If you haven't already, check out the PyCharm blog, where you'll find up-to-date information about releases and events. Now's a good time to pay attention because stuff is happening pretty fast with 2022, 2020. Is that what year we are in, Jeremy? Is this 2022? 2022.1. And events, for example, I'll be at PyCon, come see me, and educational resources such as this webinar. We'd love your feedback on this webinar. We read it, we listen, so please feel free to contact us on Twitter, or even better, the after webinar survey, which we will email in a bit for those that registered. That's all from us today. Thanks for joining. Thanks for staying with us, and hope you have a nice day. Jeremy, thank you very much.
My pleasure. Thank you again.
All right. Bye, everybody.